A loop is any closed path. You can see here, this is a closed path for current going through within the electrical circuit or going through the circuit elements. Why am I taking IR products? Because we know V is equal to I into R, and this law basically tells us about the EMF and the potential. So V is nothing but the potential. Why are we considering these B and D points? Because the galvanometer is connected across these 2 points. Now at this node, you can observe I2 is the current entering, IG is again the current entering, and I4 is the current leaving. Hello everyone, welcome to session 5 of chapter 3 current electricity. This is Swati, Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in this session, we are going to study about an important topic called Kirchhoff laws. Before that, let us understand what is an electrical circuit. So, electrical circuit, which means a systematic arrangement of the electronic components, which includes the sources of energy such as cells, a battery, resistor, or sometimes all these components are interconnected with each other in a very complicated way. So how to get solution for these complications? We can resolve this problem with the help of Kirchhoff's laws. So such interconnections of electrical components or the circuit element is generally called as an electrical network. So with the help of Kirchhoff's laws, we can get the solution for the complications in an electrical circuit. So Kirchhoff's laws are basically of two types. One is Kirchhoff's current law, the other one is Kirchhoff's voltage law. So let us now begin with a node or a junction. So to understand this KCL, Kirchhoff's current law, or KVL, Kirchhoff voltage law, we need to understand certain terms, one of which is a node or a junction. What do you mean by node or a junction in electricity? A node or a junction where two or more elements connect, it is called a node. A point where two or more elements connect, we'll call it as a node or a junction. So junction means generally it is a meeting point. Two or more elements you can see here, it is meeting at this point and we'll call it as a junction or a node. And here also in this example, this element is connected with this one and this is connected with this one. So we'll call this as a node or a junction. To understand Kirchhoff voltage law, we must know about a loop or a mesh. We oftenly use these two words, that is loop or mesh. So let us understand what is the meaning of a loop in an electrical circuit. A loop is any closed path. You can see here, this is a closed path for current going through within the electrical circuit or going through the circuit elements. So here it starts from positive terminal, so the current will pass through the circuit elements and this is a closed path. Generally we call it as a loop. Now what is a mesh? Mesh is also a loop that has no other loops inside it. So it is a loop inside which I have a loop. So a mesh is generally a closed path which has no other loops inside it. Generally current flows in a closed circuit. So loop is again a closed path for current to pass through in a electrical circuit. Now let us understand Kirchhoff's current law. Generally it is called as KCL. It is also called as a node rule or a junction rule. It states that sum of current entering the node is equal to the sum of currents leaving the node. Generally we know what is a node or a junction where two or more elements meet. So this is a node. Let I1 is the current entering the node. I2 is again the current entering the node, and this IT, or I'll call it as I total, which is leaving the node. Now according to the definition or according to the statement, Kirchhoff current law states that sum of currents entering the node. Here the two currents entering the node are I1 and I2, which is equal to sum of current leaving the node or the total current leaving the node. Here you can observe the direction. So IT is the current which is leaving the node. So this is the expression for the current to this particular example. It can also be stated as the algebraic sum of currents meet at a node is equal to 0, which means we can even write this as I1 plus I2 minus IT is equal to 0. The algebraic sum of currents meet at a point in a node is equal to 0. Let us go through another example to understand this better. So here you can observe this is a node or a junction. I2 is the current entering the node, I3 is the current leaving the node, I1 is the current entering and I4 is the current leaving. Then according to Kirchhoff current law, sum of the currents entering the node is equal to sum of the currents leaving the node. So from this example we can observe I1 is current entering, I2 is again current entering this point. So I1 plus I2 is equal to I3 is current leaving, it is in this direction, and I4 is also the current leaving the node, and that is equal to I3 plus I4. Or we can even write this as I1 plus I2 minus I3 minus I4 is equal to 0. According to the statement, the algebraic sum of currents at a node is equal to 0. What is the importance of this KCL, or what is the significance of Kirchhoff current law? It signifies the laws of conservation of charges, which is a very important point to understand. Conservation of charges can be explained with the help of Kirchhoff's current law. Now let us move on to the another law, that is Kirchhoff's voltage law. Generally it is called as KVL, or it can also be called as a mesh rule. What is the statement of KVL? It states that the algebraic sum of EMFs and the changes in potential energy around any closed loop or a mesh in an electrical circuit is equal to 0. Basically, it says about the voltage, the potential, and hence the name KVL, Kirchhoff's voltage law, where the previous law is about the current at particular junction, and hence it was KCL. Now this law states only about the EMF or potential, so it generally talks about the voltage, and hence the rule Kirchhoff's voltage law. So let us now understand this with an example. So before going to this example, there are some rules to follow. We call it as sign convention in understanding a mesh rule. So the first rule is the IR product is considered as positive when the direction of observation is in the direction of current through the resistor. Say for example, if I am observing in this direction where the current is going through the resistor, then IR product is taken as positive. The IR product is taken as negative when the direction of observation is opposite to the direction of current flowing through the resistor. So while solving the examples, we will come to know it, what exactly the sign convention is considered as. And so when is the EMF of a cell is said to be positive? So the EMF of the cell is considered to be positive if the direction of observation across the cell is from negative terminal to positive terminal. Suppose if I am observing from this side to this side, my direction of observation is from negative terminal to positive terminal, then the EMF of a cell is considered as positive. It is considered as negative if the direction of observation across the cell is from positive terminal to negative terminal. So keeping all these sign conventions in mind, let us now understand KVL, that is Kirchhoff voltage law, for a given example. Now I have considered an electrical circuit which has two loops, loop 1 and loop 2. Let us now apply the KVL to first loop, that is A, B, E and F. So this is my first loop. Let us now apply the KVL for this loop. So applying KVL, you can see here my direction of observation is like this, which means it is considered. Why am I taking IR products? Because we know V is equal to I into R, and this law basically tells us about the EMF and the potential. So V is nothing but the potential. So the IR product is considered as positive if the direction of our observation is along the direction of current through the resistor. Now I am looking at this way, and the current is also moving in this way across the resistor, then it must be positive. So it is plus I1 and R1. Now the current is moving in this direction, that is exactly opposite to the direction of I2. Then that must be minus I2 R2. The IR product is negative in this case. And here the current is flowing from this direction, say for example. Then it should be, here I have plus I1 R1 minus I2 R2, which is equal to E1. And now our direction of observation is in this direction, which means we are observing across the cell from positive to negative terminal, then it is minus E2. Now bring these terms to the other side, we get I1 R1 minus I2 R2. This plus E1, when that comes to the other side, it becomes minus E1. Minus E2 when it comes to the other side becomes plus E2, which is equal to 0. Now let us apply the same KVL to the second loop, that is E, F, C and D. Here again, I am observing this in this direction. Now, the current is moving in this direction. So, the I2, R2, IR product must be positive. So, I get plus I2, R2. Now, I am observing in this direction. So, it is just opposite to the current direction. That is, I3, R3 is in this direction. But my observation is opposite to that. And hence, it is minus I3, R3, which is equal to. So, EMF, let us say, in this way the current is flowing, so it is traveling from minus to plus, so it is E2, and here it is again coming from positive to negative, so minus E3. Now transposing this to the other side, we get plus I2R2 minus I3R3 minus E2 plus E3, which is equal to 0. This is how we have to apply Kirchhoff voltage law to the particular loops or a mesh. So now by understanding these two important laws, let us derive an important expression, examination point of view, as well as this is very important for your practicals. That is a condition for balanced Wheatstone bridge using Kirchhoff's rules. We are using KCL and KVL and we are obtaining what is the condition to balance the Wheatstone network. For that, we have considered a circuit diagram which is as shown here. Let P, Q, R and S are the 4 resistors that I have used, and you can observe here I1, I2, I3 and I4 are the currents. Some of the currents are entering one node and some of the currents that are leaving the nodes. You can just analyze from the diagram. What is G here? G is nothing but the resistance of galvanometer. IG is nothing but the current across the galvanometer. Here IG is the current which flows across galvanometer, and E is nothing but the EMF of a cell, and K is nothing but the key. Now let us understand, galvanometer is connected between two ends, B and D. So at B, let us consider B as our node. So what is KCL at B? You can see here. So I1 is entering the node B, IG is leaving the node B, and here it is I3. You can observe here. So I3 is again leaving the node B. Then according to KCL, it is nothing but sum of the currents entering the node is equal to sum of the currents leaving the node. So we can write it as I1 is equal to I3 plus IG, which can also be stated as the algebraic sum of all the currents at a particular node is equal to 0. So let us bring these terms to one side and we can get the equation I1 minus IG minus I3 is equal to 0, or we will call this equation I1 is equal to IG plus I3 as equation 1. So let us understand the same KCL at this point. Why are we considering these B and D points? Because the galvanometer is connected across these 2 points. Now at this node, you can observe I2 is the current entering, IG is again the current entering, and I4 is the current leaving. So our expression will be I2 plus IG, because these two are the currents entering, which is equal to I4. Or this can be written as I2 plus IG minus I4 is equal to 0, and our second equation is I4 is equal to I2 plus IG. Now, let us apply the Kirchhoff's second law, that is KVL, to mesh A, B, D and A, and my direction of observation is like this. So, IR product is considered as positive if the direction of observation is along the direction of current across the resistor. So, according to KVL, to the mesh A, B, D and A, we get I1P positive because my direction of observation is in this way. In this direction I am observing. So, I1P is positive and I am observing in this way. I am considering only the half of the circuit, that is A, B, D and A. My direction of observation is like this. So, IG into G, here G is nothing but the resistance and hence it is considered as IR product. So, plus IG into G, and my direction of observation is now this way, which means opposite to this current, and hence it is minus I2R, which is equal to 0. That's my third equation. Similarly, let us apply a KVL to this loop, the other half, that is B, C, D and B. Now applying KVL to B, C, D and B, we get, my observation is like this, which means it is going in this way. So Here it is plus I3Q. We get plus I3Q because it is along the direction of observation. And here you can observe I4 is opposite to our direction of observation, and hence it is minus I4, and the resistance we use here is S. So it is minus I4 into S, and the direction of observation is going along this way, which is opposite to the direction of IG, and hence it is minus IG is equal to 0. These are the 4 equations according to KCLs to particular nodes, that is B and D, and KVLs to 2 particular mesh. So when can we say the network is balanced? When the current through the galvanometer is 0. That means when IG is equal to 0. So substituting IG value 0 in the equations 1, 2, 3 and 4, we get this whole term is equal to 0. And simplifying this, we get I1 is equal to I3, I2 is equal to I4. From first 2 equations and applying IG value 0 in the next 2 equations, we get this entire term becomes 0 and we get I1P is equal to I2R. So that is our next equation, that is 7th equation. And here this whole term becomes 0, we get I3Q is equal to I4S. That is my 8th equation. Now let us divide these 2 equations. I1P is equal to I2R by I3Q is equal to I4S. And we get I1P divided by I3Q is equal to I2R divided by I4S. But here we can say I1 is equal to I3, I2 is equal to I4. Then we can write the same equation as, in the place of I1, I am writing I3 because they are equal. I3P divided by I3Q is equal to, in the place of I2, I can write I4 because they are equal. So it is I4R divided by I4S. Now we can cancel these common terms and we remain with, here I3 gets cancelled, I4 get cancelled, and we remain with P by Q is equal to R by S, and this is the condition for a balanced Wheatstone network. And by practicing these theorems again and again, you will be thorough with the expressions, and this is very important examination point of view. So in today's session, we have learnt about the Kirchhoff's rules, Kirchhoff current law, Kirchhoff voltage law, and what is the condition for balanced Wheatstone network. In the next session, we will solve numericals regarding to all these topics. Until then, keep learning all of you. See you all in the next session. Thank you.